Hi everybody, welcome back. In this video, I'm going to give an introduction to thermodynamics. So far, we have discussed kinetics, and kinetics tells us how fast chemical changes occur. We've just finished covering a huge unit on equilibrium, and that tells us how far a reaction will go. Within that unit, we learned how acids react with bases. And we have discussed a little bit about gases, especially in first semester journal in chemistry, how those gases expand to fill their containers. But why do these changes occur in the first place? Well, it's all due to entropy. I should say it's much to do with entropy. We'll discuss how enthalpy plays a role again. But entropy is related to the dispersion of energy. So let's talk about nature's heat tax. Well, the first law of thermodynamics says that energy cannot be created nor destroyed. We burn gasoline to drive a car, and some of the energy from the combustion reaction goes toward driving the car. Which is about 20%. And the rest is dissipated as heat. So you could say that the total energy that we put in is equal to the energy that we get from driving the car, in addition to the energy that's released as heat to the surroundings. Now, the second law of thermodynamics states that for a spontaneous reaction, the entropy of the universe increases. Essentially, delta S of the universe is greater than 0. So we use delta S to represent the entropy change here. And that based on the second law of thermodynamics, if we have a spontaneous reaction or process, the entropy of the universe is increasing. Well, if that's the case, we cannot break even. That basically nature is going to take some sort of tax off of all of our energy transactions. So this is kind of a cool metaphor to think about how entropy plays a role, and why, we can't break even in terms of when we utilize like energy sources, for example, to move the car. We would love that the total energy gives us exactly the amount of energy we need to drive the car, but this is the heat tax that the surroundings always takes out, that nature always takes out of every energy transaction. Think of a rechargeable battery. Well, a rechargeable battery requires more energy than the energy available to do work during discharging, because some energy is always lost to the surroundings. During the charging and recharging cycle. And for most energy transactions, not only is the heat tax lost to the surroundings, thanks to the second law of thermodynamics, but additional energy is lost because real-world processes, they never achieve theoretically possible maximum efficiency. And so if any of you end up doing research, looking for cleaner, more renewable sources of energy, you will learn that a lot of these processes just have a hard time reaching maximum efficiency, not even close. So that's something that we're always fighting against in terms of trying to create cleaner energy resources. So the most energy or efficient energy use would require the fewest transactions. That way nature can't keep taking so much heat tax off, right, for every single transaction. So, for example, if we think about heating our home, if we heat our home using natural gas, that only requires one energy transaction. Basically, the combustion of natural gas is an exothermic reaction which is used to heat our home. However, the majority of us would heat our homes with electricity. That requires quite a few energy transactions. First, the combustion of fossil fuels, which creates steam to run the turbines to generate the electricity that then needs to travel from the power plant to your home, and then the electricity runs your heater. That is 1, 2, 3, 4, 5 energy transactions, right? Compared to the one energy transaction to heat our home with natural gas. So nature's going to take its heat tax on every single of these transactions, so it becomes less and less energy efficient. So with each transaction, energy is lost to its surroundings. And that is largely due to the fact that in the second law of thermodynamics, if we want something to occur, then the entropy of the universe increases. This is an energy term. So if it's always increasing, that is nature's way of taking out its heat tax. So let's talk about spontaneous and non-spontaneous processes, since that's mentioned in the second law of thermodynamics. Well, a spontaneous process occurs without outside intervention but be careful not to confuse spontaneity which is thermodynamics, with speed, which is kinetics. So if we look at the diagram below here, this shows you a simple energy diagram where you have products on the far left, reactants on the far left, and products on the far right here. And we've learned that you have to go over an activation barrier. Now this is just showing you an example. So for example, the products are higher in energy than the reactants, so this is an example of an endothermic process. It depends if the energy is enthalpy, which would be endothermic, or if it's free energy, which we will learn later, which would be endergonic. So we'll learn about that later. But what's really interesting about this diagram, and I thought this was, when I first saw this diagram a few years back, that it was a great way to visualize the difference between thermodynamics and kinetics. Because when I was a student, I always learned that, don't confuse the two, right? They're separate. And that's why you have, you study a big thermodynamics unit and a kinetics unit, and then you just, learn it that way. But I just thought this was a great visual. So thermodynamics deals with the relative chemical potentials of the reactants and products. You're just concerned about the initial and final points of your reaction or process. That's all you care about. So that is these terms, and that's why thermodynamics, the math tends to be quite easy. We're going to be dealing with state functions where all you care about is products minus reactants, right? So the formulas themselves can be quite simple. It enables us to determine if a reaction is spontaneous or not. So for example, like I said, this probably is dealing more with a free energy diagram, and free energy for sure will tell us if it's spontaneous or not. Enthalpy, not necessarily, because we have to always take into account entropy, and we'll get to that. So kinetics involves the chemical potential of the intermediate states. It's the center point of the energy diagram. And this one's only showing, it's not even really showing an intermediate, but it's just showing the transition state. But remember, we've learned that there could be multiple. multiple intermediates, multiple transition states, depending on the mechanism. But anyways, the kinetics deals with the center part of the energy diagram. It's like that activation barrier, right? So like, for example, the higher the activation barrier, the higher the mountain to climb, the slower the reaction, right? So this allows us to determine how fast a reaction will take place, if it's slow or if it's fast. So spontaneity deals with thermodynamics, if the reaction will occur at all. Kinetics only deals with the speed. And so, for example, a reaction may be spontaneous, but could be so slow that we don't really see it proceed at all. Now, I just want to bring in the concept of catalyst. We discussed that when we learned about kinetics earlier. Catalysts cannot make a spontaneous reaction spontaneous. It only affects the activation barrier. It can lower it, which only affects the rate of reaction. A non-spontaneous reaction is not necessarily impossible. There are a couple things that we can do to help a non-spontaneous reaction become spontaneous. One way is to couple it, so we'll learn about that later on. So coupling it with another process or reaction that is spontaneous. Coupling means like we're running it at the same time and maybe they're interacting with each other. So we'll see examples of that later on. Or supplying energy from an external source. We will learn in the electrochemistry chapter that voltaic cells are spontaneous, so no external energy source is required. It will proceed to create an electrical current. However, with an electrolytic cell, that always involves non-spontaneous reactions, and so you need an external energy source to help that reaction proceed. And so that will be a great example when we study electrochemistry together. So, just wanted to review briefly. Just gave you an introduction to thermodynamics, and that a lot of times the reason why changes occur in the first place is all due to entropy. So this chapter, we will discuss entropy quite extensively. We've reviewed over the first law and second law of thermodynamics, so make sure you feel comfortable with knowing what the laws are and what they mean. We also learned that nature wants to take a heat tax thanks to the second law of thermodynamics, and so we never can break even with our energy transactions. That also most energy transactions, not only is the heat tax lost to the surroundings, but real world processes never work towards achieving maximum efficiency. It's just how it works. The most efficient energy use is through the fewest transactions, because every transaction energy is lost once again to the surroundings. And then I introduced this idea of a spontaneous process, or what we will be focusing on is a spontaneous reaction, right? As chemists, that will be our goals, to look at spontaneous reactions or non-spontaneous. And if you're spontaneous, it occurs without outside intervention. We also discussed how thermodynamics is different than kinetics. It's really important that you make that distinction. And that catalysts not only can't make a spontaneous reaction spontaneous, they only affect the rate of the reaction. However, we will learn in this chapter here that we can make a non-spontaneous reaction proceed. We can couple it with another reaction that's spontaneous, or we can supply energy from an external source, and we will see that when we study electrochemistry together. Well, thank you guys for watching, and I will see you next time.